session again. The next speaker is Arnaud Chéritat from Centre National de Recherche Scientifique and Institut de Mathématiques de Toulouse. And it is a joint work with Adam Epstein from Warwick University Mathematics Institute. And the title is Bounded Type Siegel Disk of Finite Type Maps with Few Singular Values. Okay.
Thank you. Thank you for the introduction. Thank you very much for letting me speak in this conference. I regret not copying. I hope you're having a good time there. But going to 2 conferences in a row was a bit complicated for me. So I'm giving this lecture from home. So as it was just said, it's a joint work with Adam Epstein, and we published this in a Science Journal Mathematics in a special issue in the memory of Tanley. So let me start the lecture. There. So it's about Siegel disk. So we'll quickly remind a few terms used in the field. So Siegel disk is a maximal domain of conjugacy to rotation, and a relatively compact Siegel disk is a Siegel disk which is relatively compact with respect to the domain of the map that we iterate. So it's tempting to call this a bounded Siegel disk, but I will try to stick to relatively compact. Also, the rotation number is defined by the angle of the rotation to which f is conjugated. And last, the bounded type rotation numbers. These are irrational, such that their continued fractional expansion has bounded entries. Okay, I guess probably everybody knows that, but yet just in case, I'll leave this a few seconds. Okay, so finite type maps were introduced by Adam Epstein. These are maps from a Riemann surface X to a Riemann surface Y. And it's very important in the theory that Y is compact because we want finitely parameters to deform Y. And in fact, another important thing in the definition of the map is that a set of singular values, I will not define singular values. I suppose everybody has seen that 10 times in the last and the present week. So the set of singular values is finite, okay? So that if you deform Y and deform the position of the singular values, makes a finite dimensional space. There's also a technical assumption that will not be very important in this lecture, which is that if you have a removable singularity, then you remove it, okay? So there's no removable isolated singularity. So it's a quite general definition which, for instance, includes all the rational maps, but much more. Let me remark that if you iterate a rational map, well, to iterate it, you need that the domain be included in the space Y. Then the nth iterate is also a finite type map. Composition of finite type maps are finite type maps. So yes, this also includes the transcendental entire maps in the Spicer class, and also Horn maps. So parabolic renormalization of a parabolic point of a finite type map is also a finite type map. So this gives you lots and lots of examples, in fact, of finite type maps. And they play a crucial role in parabolic implosion, in some aspect of the study of parabolic implosion. So for instance, Adam adapted many theorems to finite, Fatou and Julia to finite type maps. For instance, Sullivan's non-wandering theorem holds, and finiteness of number of non-repelling cycle holds, and that kind of things. let me remind that a sufficient condition to be linearizable when you have a fixed point of multiplier exponential to pi I theta is that theta has bounded type. So bounded type is enough. Try to use the, oops. I just need to get familiar again with this tool. And yeah, so bounded, oh, sorry for that. This is the tool I wanted to use, bounded type. And this was, in fact, Siegel proved a theorem which was slightly stronger. And later, Buono extended this theorem to a larger class of numbers, which I will not define today. And so that was the reminder. So now I'm going to state the main theorem. It's a bit long and complicated. And then I will give a simple, explain a simple case of the theorem. And then I will come back to the theorem in more details. So we will see this statement again later in the talk. So the theorem, I'm just going to read this theorem aloud. So you take it's taking place in the Riemann sphere C hat. So and the starting set, the stated definition of F, I will call it U from now on. So F is a map, finite map from a subset U of C to C. It's holomorphic with finitely many singular values. U is open. And here's the assumption. So first, the singular set has cardinality at most 3. Okay. So this is why the lecture is called about what was the name of the lecture? Siegel disk of finite maps with few singularities. So few means at most 3 here. Moreover, in fact, the fixed point must be in A, B, C, which means that if I rephrase it, cardinality of the fixed point of the fixed point A. This is a bit cardinality of A. A is the fixed point. Union singular set. Is at most 3. Okay. We assume that the rotation number has bounded type, and there's another supplementary assumption, which is that C is not in the domain of definition of F. Or we were able to extend the theorem to the case of a point in the domain of definition, provided it's fixed by F. Okay. So up to now, I don't know if we can extend it further. These are technical assumptions, but they find applications enough, at least for the use I wanted to make of this. So now there are 3 possibilities, and which are listed below. Okay, maybe you've had time to read or not, but you consider an injective path from the marked point A to the marked point B. And this point should avoid A, B, C, except at the ends, of course. And you're going to lift this path. So since A is a fixed point, which is not critical, there is a unique lift by F that starts from A. Call this lift gamma tilde. So you have this lift gamma tilde, and then you're going to look at the endpoint of gamma tilde. So it starts from A, but where does it end? So maybe it ends on the non-critical point. This is case 1. This case is very restrictive because then U must be C hat and F must be a homography. So with a very boring dynamics. Or gamma tilde ends on a critical point. Then that's the case I'm most interested in. Then the conclusion is that delta is a quasi-disk and that its boundary contains a critical point, but no other critical point. So which critical point? The one at the end of gamma tilde. And the third case is also interesting. It's in the case that gamma tilde doesn't converge in U. Then it has to leave every compact set of U. It's not hard to check that. So only case 1, 2, or 3 are possible. And then the conclusion is that the Siegel disk delta does not have compact closure in U. Yeah, forgot to write in this slide that delta is the Siegel disk. Okay, so that's a long statement, but we'll come back to it. But first, I will give a bit of context, historical context, if you like, but very, very quickly, because time flies. So first, well, Siegel disk, the dynamics inside a Siegel disk is just a rotation. So even though rotations are not that simple to study, if you study them very closely, they can be considered as quite boring. But what happens at the boundary? So what happens at the boundary of a Siegel disk is much more interesting from my point of view. So, for instance, is the boundary a Jordan curve or not? And if it is a Jordan curve, is it smooth? Does it contain a critical point? Or that kind of questions. So first, the first examples of Siegel disks, of non-trivial Siegel disks, is, for which the boundary was understood, where for degree 2 polynomials, thanks to quasi-conformal surgery that I call the GIS surgery, because the initial idea is due to Etienne GIS, and then it was adapted by people. So thanks to this surgery, Hermann was able to prove that for some rotation number, the quadratic polynomial has a Siegel disk, which is a Jordan curve, whose boundary is a Jordan curve. And this Jordan curve doesn't contain the critical point. Later, Perez-Marco was able to produce a smooth Siegel disk. So this Siegel disk was not for a polynomial map, it was for an injective map from a subset of C to C. So not even a transcendental map, but the boundary was smooth, which could be seen as a surprise at the time. And so with Xavier Buff, I extended this result to, we were able to modify the proof so that we get smooth Siegel disk in the quadratic family of degree 2 polynomials. And then Avila came and simplified our proof, and which allows to extend this and to prove that in almost every family there is a smooth Siegel disk. Very interesting result. So, okay, so but let's come back to earlier times. In fact, the GIS surgery procedure was extended from case 1 to case 2, following ideas of Douady and equalities by Schatek and work by Hermann. So they were able to have an example which is a Jordan curve, in fact, a quasi-circle with a critical point on the boundary. So, and yes, in fact, the Jordan curve in the quadratic family, you can have not only smooth Siegel disk, but C1 Siegel disks that are not C0, or C4 Siegel disks that are not C3, or any kind of regularity. You can also have Siegel disks that are not quasi-circles at all, provided you, in these examples, it's always the critical point never belongs to the boundary. With the technique that we developed with Buff, it is not possible to have the critical point in the boundary. And last result I wanted to speak about before going into the subject was about non-locally connected Siegel disk boundaries. It wasn't known for a long time whether or not there could be bounded, relatively compact Siegel disk with non-locally connected boundary. And the answer is yes, it's possible. So using an idea of Hermann, which almost did it, I was able to modify his proof to get an injective map from a subset of C to C with a relatively compact Siegel disk, whose boundary is a pseudo-circle. So a pseudo-circle is a very complicated set, which in particular is not locally connected. Okay, so but today we will focus on the DG's surgery procedure, and so I'm going to especially focus on case 3. So let's. Oh yes, of course I'm not going to cite everybody because there's too many people, and I will probably forget somebody if I try to be inclusive. But let me at least state that these works have been extended by Shishikura, Peterson, Zakiri, Jean Gaufey, Rush, Gratchik, Jones, and many other people. And also about the tools. When I worked with Buff, we used the Yoko's renormalization. Okay, it was a central tool. And using other kinds of renormalization, there have been works by Yampolsky, Shishikura, Ino, Shiragi, and several other authors, which allows for Siegel list of quadratic maps to get much more information, especially information on the post-critical set. And but I don't have time to review. It's not the topic of this lecture. And also, quite recently, there has been a new approach to study Siegel list of quadratic maps with snakes and white rectangles, and this looks quite exciting. And it's by Dimitri Dudko. Okay, so but let's go back in time. And let me cite the following theorem because it will play a role near the end of this lecture. And so it was quite interesting when it was announced. So if you consider a map whose Siegel is relatively compact and whose rotation number has bounded type, then necessarily there is a critical point on the boundary. Okay. Therefore, it's reproving part of case 3, which concerned quadratic polynomials, because their Siegel disks are always bounded. But this theorem does not tell you that the boundary of the Siegel disk is nice. Okay, it could be non-locally connected, it could be the whole Julia set, probably, in fact, not, but it could be not a quasi-circle. In fact, it is a quasi-circle, but for other reasons. Okay, so this theorem doesn't claim anything about the regularity of the boundary of the Siegel disk. It just tells you that there must be a critical point. So the proof was using a normalized Schwarzschild derivative of the conjugacy from the rotation to the map, and some area estimates, and also properties of invariant functions. So very clever proof, and which I will not detail here, but I will refer to this theorem later. Okay, so now we go back in time again, in the late 80s, sorry. So there is this surgery theorem. I already said it aloud, but it wasn't written on the screen yet. So if you take a bounded type rotation number and the quadratic map polynomial that has this rotation number at the fixed point, then there is a Siegel disk, and its boundary is a quasi-circle which contains the critical point of the polynomial. Okay. So this is the central theorem that we extended progressively until we got this theorem with Adam Epstein. So here's a picture that's resuming the Douadi surgery, but in fact, we'll come back to this picture later. I will detail the surgery here for 10 to 15 minutes, because that's the surgery that we will adapt. So here's how it goes. So you start from a Blaschke fraction. So a Blaschke fraction is a fraction of Blaschke products. So here it's z squared divided by some automorphism of the disk. Which with parameter 1/3. So therefore, f sends 1/3 to infinity. So f is not preserving the unit disk. Okay, it's mapping points in the unit disk outside. So here is drawn the unit disk on the right, and it's pulled back by f. Is shaded in gray here. So there are two components. One is mapped 2-to-1 to the unit disk, and one is mapped 1-to-1. Okay, so 1-to-1, and here it's 2-to-1. And that's mapped to infinity. Some point here, 1/3. That's 0. That's 1/3. Okay, so yeah, it's appearing in the next slide. So maybe I can try to copy this. This is no, is it? Yes, it's a selection. So if I'm lucky, it will copy. Yes. Okay. So this preserves S1, but not D. So the boundary of the unit disk is mapped to the boundary of the unit disk. That's what it means. And moreover, F is injective on the unit disk. So on the unit circle. So on the unit circle. So therefore, it's a homeomorphism of the unit circle. It's analytic. So but it's not a diffeomorphism because 1 is a critical point of local degree 3. So 1 is mapped to 1, but with local with derivative 0. Okay, so it's called an analytic homeomorphism of the circle. It's also called sometimes a critical circle map. So critical circle maps for the people working in these fields in this field is analytic homeomorphism of the circle with at least one critical point. Okay, so for the theory of critical circle maps tells you that for all irrational rotation number, you can find a unique rotation such that if you post-compose F restricted to S1 by this rotation, then the map you obtain has rotation number theta. Okay, so there's a unique parameter such that the rotation number of this modified map rho F has rotation number theta. So from now on, I just realized something that from now on, let me on the next slide. Okay, so sorry. So if you look at the restriction of F to S1, there's this theory by Poincaré that there is a semi-conjugacy to the rotation, but in fact, Yokos proved that since F is analytic, even though there is a critical point, in fact, the Poincaré semi-conjugacy is always a conjugacy, is always injected. And moreover, Schottek and Hermann, they proved that the map H is quasi-symmetric. I'm not going to define what quasi-symmetric means, but it has a very nice consequence. It's that, in fact, this quasi-symmetric map from S1 to S1 has a quasi-conformal extension to the unit disk. Okay. In fact, a quasi-conformal homeomorphism of the unit disk to the whole unit disk necessarily extend continuously to the boundary to a quasi-symmetric map. And conversely, Alfors and Berling proved that if you have a symmetric orientation preserving map of the boundary of the unit disk to itself, then there is a quasi-conformal extension inside. In fact, Douady and Earle later reproved this with some interesting feature, but that I will not use. So I'm not going to state the Douady-Earle theorem. Yes, so on the previous slide, I realized that I forgot from now on to put a row in front of F. So now the map is not F, it's row F. So in other words, from now on, F will refer to row times the previous F. Sorry for that. Yeah, if there are any questions, of course, you can speak, and I will be happy to answer those questions. So here's our situation. So let's first, so now we're going to make a surgery. So we're going to modify row F. So for this, we start from removing, we have removed the unit disk from the domain of F. So now the unit disk is not anymore in the domain of F. And then we will use H tilde to plug the rotation inside the unit disk by conjugacy. And since H is a conjugacy on S1, this will define a continuous map. And since H is quasi-conformal, this will define, in fact, a quasi-regular map on the top picture. So the next slide explains this. So F tilde is an extension of rho times F on which we removed the unit disk, and we plugged the conjugate of the rotation by H tilde. And F tilde is quasi-regular. And here I had my computer. So I made this nice computer experiments a few days ago, which I never did before. I actually had the computer compute the Douady-Earle extension of H of the semi-conjugacy for the bounded type rotation number golden mean, for the golden mean. So for the golden mean, it looks like this. By the way, the previous graph was this graph was the graph of H for the golden mean. So it's quite non-differentiable. And this map, the Douady-Earle extension, is real analytic, maybe at least C infinity, and maybe real analytic inside. But it doesn't preserve the conformal structure. You can see the origin is mapped here, and its circles are mapped to ellipses somehow. Well, so I don't know what to do with this picture, but yeah, you may find it interesting or not. Okay, so there is an invariant Beltrami form for F tilde inside the unit disk, which is just pull back the field of circles, the trivial Beltrami form on the bottom part. You pull it back by H tilde, you get a non-trivial Beltrami form on the top that is invariant by F tilde. F tilde in this picture will the orbits on their F tilde will be those circles that you see here. Okay, anyway, then the rest of the argument goes as follows. We have defined invariant Beltrami form in the unit disk, but it's not defined outside, okay? So we will extend this Beltrami form into a F tilde invariant Beltrami form by a classical rollback argument. First, pulling it back to the first pre-image of the unit disk by F tilde, and then to further pre-images and so on and so on. So the picture looks like this in the end. It actually looks like this, and and outside this union, you just set mu equals 0. then it's invariant by f tilde, and f tilde is quasi-regular. So now you can straighten the Beltrami form and conjugate f tilde by the straightening. This straightening will preserve the zero Beltrami form, therefore the straightening will be holomorphic. That's classical holomorphic surgery that I'm describing here. So when you conjugate using Alfor's best theorem, but in fact it was first proved by Moret in this degree of generality of non-continuous mu. The conjugate is holomorphic and has a Siegel disk, has a rotation domain with rotation number theta, and it's also a 2-to-1 covering, ramified covering of the complex plane. Therefore, it has to be a quadratic polynomial, and there's only one up to conjugacy, up to a fine conjugacy polynomial with those features, which is exponential 2 pi I theta z plus z squared. Okay, so that's the Douagi-Gis surgery and made functional by Hermann and Schatek, and therefore the straightening S does conjugate the top picture to the bottom picture. Of course, I'm not able to compute by a straightening map by numerically. I just drew the Julia set of the quadratic map below, and the picture before is part of the Julia set of the map F. Okay. When they are case inside the unit disk, I stop iterating. Rho F. So it's possible to produce those pictures, and S, the straightening S, sends the top picture to the bottom picture. In particular, it sent the Siegel disk is the image of the unit disk, and since the map S is quasi-conformal, the Siegel disk boundary below is a quasi-circle, obviously. And the critical point is on the boundary on the top, therefore the critical point is on the boundary below, and you can prove much more. For instance, Peterson proved that the Julia set on the top, the Julia set of F tilde of the quasi-regular map on the top is locally connected, therefore below the Julia set is locally connected, etc., etc. So lots of things have been proved thanks to this surgery. Okay, so now I'm going to make a remark that will allow us to generalize this to further maps. Okay, so let me point out that the map F tilde that we have defined, so let me recall, it's quasi-conformal inside the unit disk, and it's holomorphic, non-injective outside the unit disk. And outside the unit disk, I want to decompose F tilde, which is the same as F. So outside the unit disk, you have in fact a conformal map finite that sends the complement of the unit disk to the complement of this set over there. Okay, so here you have your unit disk, here you have a set. You send the complement of the unit disk to the complement of you send the H set to the H set. Okay, finite. There's not enough room between those two pictures. And what is this lemniscate? It's just a preimage of the unit disk by 1 minus z squared. So we have this commutative diagram. In fact, you can extend this commutative diagram inside the unit disk by appropriately choosing phi naught from the unit disk to this part of the lemniscate, to the left part of the lemniscate. You can choose phi naught so that the diagram, in fact, commutes on the whole complex plane. So F tilde is cover equivalent to z squared, to the polynomial that we want to model with F tilde. And but on the exterior, we have this nice conformal map, and this is important. So note that F can be recovered. So the map F tilde is F modified inside the unit disk. So if you want to recover F, knowing only F tilde outside the unit disk, So imagine you know F tilde just outside the unit disk. It's a holomorphic map to the whole complex plane. Well, since it sends the unit circle to the unit circle, F, which was the original map, preserves the unit circle. So you can recover it by Schwarz reflection, which means that the Schwarz reflection of the drop on the right is this red curve that I just drew, and you recreate F. Okay, so further developments. With using this idea, I will explain you in a minute how I use this idea to generalize the construction, and this allowed me to adapt the Dwadijis surgery, quasi-conformal surgery, to Horn maps of quadratic polynomials. And this was important in the proof of existence of positive measured Julia set. The initial proof, then the proof was modified later, but the initial proof used that. And also a bit later, I wanted to extend this to some entire maps. And thanks to a discussion with Dirk Schleicher in a long time ago, we were able to determine which class of entire functions this trick would adapt to. So in particular, it gives uncountably many examples, which is nice, thought at that time. So this was published in 2006 together with the Horn maps. But on the same year, in 2006, I presented at the birthday conference for Dwadi, the 70th birthday conference, this proof, and Adam Einstein was in the room, and he noted that in my argument, I was using some rigidity of the quadratic polynomial, an argument that in fact was not necessary. He explained to me how you could use a homotopy argument instead. That I will explain near the end of this lecture. Okay, so how do you adapt the surgery? What's the idea? So the idea will be a construction that starts from a map with a fixed point and few singular values. And from this map, we construct, using uniformization and Schwarz reflection, a model, a pre-model. So it's because it's a map that preserves the unit circle and has a symmetry. It's symmetric with respect to the unit circle. So we modify it inside the unit circle by a quasi-conformal rotation, and we get a quasi-regular map. Here it's quasi-regular. And it has an invariant Beltrami form. We straighten the Beltrami form and conjugate the quasi-regular map, and we get a holomorphic map, a new holomorphic map. And we pray, maybe we are lucky, and this map is the same as the original map. In some cases, at least it is. So here's a description of the procedure. So there's a lot of spheres on that screen. So let's start from the one on the lower bottom, middle bottom row. It's a sphere with 3 marked points. Okay, A, B, C. Okay, so A, B, C, A, B, and C. And soon I will take A equals 0, B equals 1, and C equals infinity. Anyway, we start from an initial map. So the initial map is given here. We need a name for it. It's a map we want to, well, I won't give it a name. Okay, so it's a holomorphic map which satisfies the hypothesis that there's the set of singular values is contained in ABC, and it fixes A. So this point is A, this point is C. C is outside the domain, so U, the domain is in yellow. And if you pull back, if you take the pre-image of the unit disk, it has many components. If you take the component that contains A, then F, this map has to be 1-to-1 on this component. And we make the assumption that there is a critical point on the boundary and only one. So this critical point is here. It's not equal to B a priori, it's some B prime. Okay. And F has a Siegel disk at the origin, and we don't know where the Siegel disk sits in this picture, but because here all those curves are analytic piecewise analytic arcs. Okay. Because it's the pre-image of the unit circle going through B. If you put C at infinity, take the circle of center A and going through B. It's the unit circle if you choose A equals 0 and B equals 1. Okay. So you pull back this unit circle. It's a complicated graph on this domain U. So what's the next step? How do you get the pre-model? Okay. So you remove this pre-image of the unit disk. So this set over there that I've crossed out, you consider the complement of this set. And you map this conformally to the complement of the unit disk. So I'm going to draw I think it's from the complement of the unit disk to the complement of the set I've removed. Finite. Okay, so finite fixes infinity and maps conformally the complement of the unit disk to the complement of this drop over there. And the pre-model, you start from the composition. So you compose finite with the initial map, and then you do Schwarz reflection. And you get a map defined on a set now that contains the unit circle and goes beyond, and sends the unit circle to the unit circle, and has a unique critical point of local degree 3. So those curves there, they extend inside with a loop and so on. Okay, so that's the pre-model. Then, yes, the Schwarz reflection was here only to justify that the map is analytic on the unit circle. In fact, you don't need this Schwarz reflection to define the model, because immediately you remove whatever is inside the unit disk, and you replace this by a quasi-conformal rotation. This gives you the model map, F, which was called F tilde in the previous slide. Then you straighten the invariant Beltrami form S, and you get a new map, G. And the orange part is mapped to, let me choose some orange. I don't remember, yes, it's there. So here it's orange. It's the Siegel disk of G. So G has a Siegel disk, which is the image of the unit circle by a quasi-conformal map and goes through a critical point. And the big question is the domain of G the same as the domain of the initial map? Is the map G equal to the initial map? Well, I think the answer is not always, but if you take a map with only 3 singular values, then the answer is yes, provided C is not in the domain or C is a fixed point. That's the point. Okay. Any questions so far? So
I think there are no questions,
yeah.
but let me remind you that you have just 3 minutes.
Okay. So yes, don't worry about this number over there. The map G as the covering is equivalent to the initial map we have started with, and G is analytic. So really the problem is to prove that the domain of G and the domain of U are identical, in fact. And this a priori is not obvious at all, because when you apply finite, you modify the domain. The conformal map doesn't preserve U, and then you straighten this. Why on earth would you get the domain of S of this thing equal to U? Okay, so this was explained to me by Adam Stein. If you have only 3 singular values in the sphere, this is a rigid situation, and you have a quasi-conformal homotopy to the identity of S relative to ABC. So you're going to pull back. Let me skip a few slides to the argument, to the pullback argument. So basically, you have that kind of commutative diagram, and you look at the outer part of the diagram. So sorry, since I was running slightly late and not watching the clock, this will go super fast. I'm sorry for that, but look at the outer part of this commutative diagram. And this gives you something like that. You have this straightening S, you have the map. So F is the initial map, and G is the map you obtain, and the objective is to prove that F equals G. And so we have defined some special map T over there. Sorry. And now you take a homotopy, isotopy from S to the identity just by multiplying the Beltrami form that S straightens by number T between 0 and 1. That's the classical way of doing a homotopy. So you define mu T equals T times mu, and you straighten mu T, you call this ST by fixing A, B, and C. So you do everything relative to A, B, and C. And then you can pull back this isotopy by the diagram. But the trick is to pull it back starting from T equals 1 and the map T1 equals T. Okay, so here I'm going to skip all the details. And you perform this pullback, and when T goes down to 0, below you got down to identity, and on the top you got down to a map T naught, okay, which is only defined on U and maps to U tilde. And the objective is to prove that U equals U tilde. So the objective is to prove that T naught is the identity. So for this, there are some arguments which I don't have time to develop, but somehow you're basically you're going to use Rickman's lemma and extending T naught using the initial map T on the exterior, and the fact that T on the exterior is holomorphic, and therefore you can prove that T naught is holomorphic everywhere on the Riemann sphere. So a holomorphic map on the Riemann sphere is a homography, and then you prove that this homography is the identity. So the last slide was to prove that the homography is the identity, and for rotation number reasons and the fact that it's fixing 0 and infinity, and therefore F is the F equals G in the end. If I'm ever able to draw, yes, F equals G, and we have a model for G. And yes, and I'm not going to show the last few slides. I would just like to thank you for listening to me. And if you want more details, well, you can see my our article, and also I will send the slides to the organizers. Thank you.
Okay, thanks a lot for a very interesting talk. Some questions from the audience first?
I have a question.
Maybe online participants? Yes, Mathieu, you can ask.
So in this argument that you did not attempt to explain is it necessary at this point that you have only 3 singular values, or is it something that you use somewhere else?
I'm sorry, Mathieu, the sound is terrible and really can't understand.
Sorry. Is it better?
Yes, much better.
Okay, sorry. Yeah, so in this argument with the homotopy that you did not have time to fully explain, is it at this point that you use the fact that you have only 3 singular values, or is it?
Yes, because if you had more than 3 marked points, when you let me come back to this picture. If you have more than 3 marked points, when you perform the isotopy to identity, the marked points move in moduli space, which means that their cross ratio will change. Okay, S has no reason to preserve the cross ratio of the 4 points or more. Okay, and therefore this goes into the way of the proof, actually, because in the homotopy lifting argument, we want those points to be fixed, to be immobile. Okay, otherwise it's impossible to pull back the homotopy S and to make the argument work. You will have to go into the details to see actually where it breaks.
Okay, thank you.
Well, to keep it short, the map F and the map G, since the cross ratio is not the same, they can't be the same. That's another argument.
Could you briefly show the slide number 29?
Yes. There.
It's 26.
Yeah.
26.
29 here. Okay, yeah, thank you. I'll read briefly.
Yeah. Other questions? Yeah, so what I did not have time to explain is case C, because I was what I've been explaining most of the time is case 2, when the gamma tilde, the pullback of gamma tilde ends up on a critical point. But case 1 is very easy to deal with, and case C has a very interesting technicalities that forced us to adapt the proof of Grachik and Swiatek, and that's what this slide shows.
Okay. Thank you once more.
Thank you.